strong law for renewal process. Recall strong law of large numbers. What does it say? Let xi be IID random variables, a sequence of IID random variables with expectation of x finite, then you have Sn over, so you have Sn over n, which is defined as xi equal to expectation of x almost surely, right. Sn over n converges to expectation of x almost surely, right. This is the strong law of large numbers for IID random variables with finite mean.
So there should be limit in the middle of.
Yeah.
There should be limit in the middle of.
Yeah, of course. Correct. This is what strong law says. So, if you take in a renewal process, xi's are just some non negative well actually positive IID random variables, and Sn corresponds to the nth arrival epoch. So, if you take the nth arrival epoch divide by n and send n to infinity, you will get expectation of x almost surely, right. It is a straight consequence of strong law of large numbers. Now, the strong law for the renewal processes is written not for Sn, but for Nt. Okay. So, let me write down theorem for a renewal process with mean inter arrival time expectation of x equal to let us say x bar. We have limit t tending to infinity n t over t is equal to 1 over x bar almost surely, and this is true even if x bar is infinite. Okay. So, for the strong law, the plain strong law for IID random variables, you need a finite mean for Sn over n to converge to expectation of x almost surely. For renewal process, Nt over t converges to 1 over x bar almost surely, regardless of whether x bar is finite or infinite. Okay. We will only be bothered with the case where x bar is finite. Okay. This is true even for x bar infinite, and the way you prove that is prove it for the case when x bar is finite, then use a truncation argument. Okay. So, this our job is to prove this theorem, all right. Let us first pictorially see what this is saying, all right. So, recall that if you look at a plot of NT versus time, you will get some kind of a step, right. At every arrival you have the process steps up by 1, correct. So, this is let us say NT omega 1, right. For some other value of omega you could have a different step function, you will have right, this is a process NT omega 2, all right. This is a different sample path of the process. So, you are taking NT of NT over T, which means that for each sample path you are looking at n of t comma omega over T, correct. So, for each fixed omega, n of t comma omega is some function of time, is a step function, right. You take n of t omega over t, all right. What we are saying is that if you send t to infinity, n of t comma omega over t will converge to 1 over x bar for a set of little omegas lying on a set of probability 1. On a set of probability 1, n of t comma omega over t goes to 1 over x bar, okay. And the set of n omegas where n of t comma omega over t does not go to 1 over x bar, does not converge at all or converges to something other than 1 over x bar, has total probability 0, that is what this is saying, okay. To be more explicit, you can, if you want, you can plot the n of t omega over t as a function of time, right. So, if you do that, sorry. So, how is n of t over t going to look? Okay. The first arrival occurs, it is going to jump, right, and then it is going to decay, right, then it is going to jump again going to decay, right, it is going to keep doing that, but the value of the jump is going to get smaller and smaller. Why? Because you are going to increase t, right. So, every time there is a arrival, this n of t. So, I am here plotting not n of t, but n of t upon t over against t, right. It is clear, no, I do not think I drew very well, but every time you get an arrival you get a jump, but the height of the jump will be not 1, but how much 1 over t, where t is that arrival the time at which the arrival happens, right. So, this what we are saying is that as time becomes very large, this guy settles at the height at which this guy settles at is 1 over x bar, okay. So, in a different sample path you could have and so on, right. But in almost this is guy is the purple guy is omega 2, the blue guy is some omega 1, right. What we are saying is that this function which jumps up and then say comes down, jumps up and comes down, this guy will settle at 1 over x bar for almost all omega, meaning that on a set of probability 1 this function will converge to 1 over x bar, okay. That is the intuitive meaning of what this strong law of large numbers is saying. Is that clear? So, this 1 over x bar can be thought of as the rate of a renewal process. So, now n t over t is the total number of arrivals in time t, right, per unit time, right, because n t is the total number of arrivals in 0 to t, you are dividing by total time t. So, n t over t is the number of arrivals per unit time, and as t becomes large, this is equal to 1 over inter arrival time, right. So, this 1 over inter arrival expected inter arrival time is the rate of the process. Okay. So, 1 over x bar has the interpretation of the rate of the process. Okay. For a Poisson process, of course, this is true, right, because well, I mean Poisson process is just a renewal process, right, and 1 over x bar there is just 1 over lambda, which is the rate of the process. Okay. So, let us try and prove this. Okay. So, let me draw this picture. So, this renewal process is running 0. So, let us say this is my t. So, at time t they have been n t arrivals, all right. Now, can someone tell me what is the time of arrival of the most recent time, the most recent customer arrival, right? What is the time of that arrival? So, n t is the number of arrivals that have come, right. So, what is the arrival epoch of the most recent arrival? S, what is n? So, the if n of t is a random variable, right. So, what is the time of the arrival which came, epoch of the arrival that came the most recently? So, at t there have been n t arrivals, right. So, when did the previous arrival come? S, S n t, right. S n t is the epoch of the most recent arrival, correct. No, it is not clear. See, suppose n t is equal to n, right. So, there have been n arrivals, you look back to see when the most recent arrival came. So, is the S a little n, right. So, S n t is the epoch of the most recent arrival. Likewise, what is the epoch of the arrival that is going to come next? S n t plus 1, S n t plus 1, correct. Correct. So, if I take, so this much is clear, right. So, I just want to build up an intuitive argument first. So, if you look at this n t over t, I can write this as being sandwiched between let me see. So, I can I write this is this correct? I am making the denominator smaller, so that this ratio can get only bigger, correct. And likewise, I can write n t over S, is that correct? So, this you will agree, right. So, now I want to make t very large, right. If I send t very large, I want to see what happens to n t over t, but for, so this is true for all t greater than or equal to 0, right, let us say all t greater than 0. Okay. So, if I send t very large, this nt over t, which is the quantity of interest for me, is going to remain sandwiched between these two things, right. So, if I want to prove that nt over t goes to some limit, it is enough to show that the thing that is sandwiched between is also going to that limit, then I am done, right. By sandwich theorem I will be I would have finished what I was finished showing what I want to show. Now, so let us look at this object and that object. Okay. So, let us look at this. As t becomes large, what does this behave like? So, first when the first arrival comes, this will be 1 over S 1, right, then 2 arrivals will become 2 over S 2, right. So, if you have little n arrivals, it will become n over S n, correct, but as t becomes larger and larger there will be more and more arrivals, correct, and n t will go through all the positive integers, correct. So, this should behave like what? N t over S n t will behave like n over S n, right, where n is going to infinity. So, intuitively n over S n should converge to what? So, S n over n converges to x bar by strong law, right. So, n over S n should converge to 1 by x bar, right. So, I have told you some 2-3 things which are not, which I have not fully rigorously justified, right. First is that if S n over n converges to x bar, should n over S n converge to 1 by x bar? You have to prove that, it is true, but you have to prove it. Okay. The other is that as t tends to infinity, you need n t to be getting larger and larger, it has to go through all the integers and go to infinity, right. So, first of all you have to prove that as t tends to infinity, n of t tends to infinity almost surely, right. So, if I do those two things, I will be done, right. So, we need a couple of lemmas here, and then we use these two lemmas, the first lemma being that n t goes to infinity as t goes to infinity, the other is that n over S n goes to 1 over x bar almost surely. So, actually it is true for any continuous functions, if x n converges to let us say some alpha almost surely, then f of x n will converge to f of alpha almost surely for all continuous functions f, okay, that we can prove. Okay, if these and 1 over the reciprocal function is a continuous function, right. So, that is all that these two ingredients we need to prove this. Okay.